more in detail about group compositions. Now, we will continue where we left the last time. So, we are dealing with the waveguides, and with the waveguides, we did the transverse electric field. So, we did the TE waves, and the TE waves, transverse electric fields, they were such that Ez was equal to 0. Assuming that the propagation of the wave along the waveguide is along the z-axis. So we have aligned the waveguide or the tunnel along the z direction. Then we did the TM wave. So the TM wave, it is similarly, this includes that Hz is equal to 0. And then we noticed that both for the TE wave and the TM wave, we had modes, right? So we had modes for either one of those, which were described in the dependency of the H factor as a function of M. Okay, so H, it was a factor which was relating the. So this H, it is a function of the propagation gamma and the frequency of the wave. Then we notice that for the Tm mode, for which m is equal to 0, we get a TEM mode, okay, which is transverse electromagnetic field. So we can have a waveguide where the E and the electric field and the magnetic field, they are both on the XY planes, okay? Because this is the case when if we have a propagation of the wave along the Z, the TEM, this is including an electric field which is lying here, and the magnetic field which is going to point like this. Then this is the electric field. And then a special case, what would be is or that we can assume the following: E is equal to E0 AX e to the power minus j beta z. H could be H0 AY e to the power minus j beta z. This is one possible option. This is an acceptable pair of electric and magnetic field intensities, which both they propagate along the z-axis, and we have also the E cross H. This is equal to AZ. Okay, so this shows the direction how they might propagate. A different way for the waves to have is also this other possibility, where we can have here E0 times AY plus JAX times e to the power minus j beta z. And what would be the H? H would be H0 times, so this is a little tricky. How to find these? We always know the longest path, the most structured method to determine one of the fields from the other one. We know that the best solution would be the following. So if we have the E, the H would be equal to minus J. I forget how this one, maybe this is minus 1 over J omega. So how is this going to be? Derivative of this one. I think here we have a mu curl of E, right? So in this case, we have AX, AY, AZ, derivative with respect to X, derivative with respect to Y, derivative with respect to Z. And then what are the amplitudes for E? Here we have for AY, this is E0, e to the power j something. And here we have J times E0, e to the power j beta Z. And here the last component is just equal to 0. If we do this, then we might expect something like this, which is going to look like this. Here we would have the J AY plus AX times e to the power minus j beta z. This is the case because the electric field AY, it is linked with the AX for H. Okay, so there will be just a shift of these components, and you can prove that this is the case if we input in here. One other thing that we may need to check is the signs. So the general picture is going to look like this, but probably the direction fields, they might be wrong. We can check those. So here we have AX is going to be coupled with this, okay? So AX with A, this is AX, AY, and AZ. So we have E cross H, this cross this. What is wrong here? This is AY cross AX. We should get plus. In order to get a plus here, we should have a minus sign in here. Okay. And then, in order, when we get the cross product between these, I think this is good. Okay. Scenjat këtu e rregull, përveç se kjo do të jetë me minus. Sepse ne duhem që gjithmonë, we need this one to always be satisfied. Okay. So now, these were what we did so far. Now, what we need to have in order for our waveguides, assuming that we can have different modes, and different modes, they are represented by different values of m. Okay, so a mode is defined by the m, of which the value of h obtains discrete values. Here we can have different discrete values, and we should not forget that the waves in the waveguide, we want them to be propagating, okay? So we want a propagating wave. But now, what is a propagating wave? Let's look at the propagation coefficient, which is gamma is alpha plus j beta. So, what does the alpha correspond to? What is alpha? So alpha is the attenuation constant, okay? And beta is the phase constant. So, as we have mentioned before, apparently, since this alpha is the attenuation constant, we remember that electric fields, if alpha is different from 0, then used to look like this: E times E0, e to the power minus alpha z, e to the power j beta z, right? So here, this was the attenuation constant, and in principle, we don't want this. We want a propagating wave. So what this means is that we like to have a situation where alpha converges to 0. So what does this mean then? This means that the gamma itself, this factor, we want this one to be defined as a purely complex number. Okay, so this is what we want in order for the wave to propagate through the waveguide. Otherwise, it will be attenuated, and then the amplitude will exponentially decrease. So in a few meters, the signal will be lost. Okay, we don't want that. We want that this factor here, this is a purely complex number, and let's remember a little bit. So let's write down one TE wave, because we just did this the last week in the previous session. So an example of a representative wave, which can be described by the electric field intensity, can be written as such: C1 sines m pi over a times x times e to the power minus gamma z. Now, this minus gamma z, we remember, we're talking about...
Sorry, camera open?
Oh, sorry? Okay. Okay, this is a little better. So this is how the wave is going to look like. The gamma that we're talking about, we have it right here. And this is the phasor notation. And as we said, the EY as a function of z and as a function of time, which will include the instantaneous expression, this can be described as a constant C1 time m pi over a x times cosine omega t minus beta z. In fact, here we should include also the x, because since this is a waveguide, so far we are used to cases where the electric field or the magnetic field intensity was changing only as a function of the orthogonal direct or the propagation direction. So the wave is going along the z. This used to be only a function of z. But now that we need to satisfy also the boundary conditions, which means that we need to make sure that if we have a waveguide that goes like this, we want to satisfy also the boundary conditions, assuming that this is along the x. So we want the electric field at the bottom part and at the top part. Often they are equal to 0, because we are discussing the waveguides which are made of metal, made of conductors. But now here we have a very tricky point, which is the following. The wave before it was, we have seen this like this, right? ZT. That was it. Now that we are constraining it into a waveguide, the situation, this is a very essential change, because now the requirement to satisfy the boundary conditions, it will constrain largely even the frequencies that we can transmit through. Okay, it's not that the waveguide is absorbing the power. No, it's just that the boundary conditions are not satisfied. Okay, so the boundary condition, the BC, the boundary condition, it limits the frequencies. Okay, so we are discussing so I want you to have a look at carefully at this, what we have here in the board. It looks like the metal walls, the boundary conditions, are going to change slightly all the conditions. Now, theoretically, this is how the changes are going to be introduced in whatever we know so far. Now, to see it better, let's have a look at what the H was. The H, this is equal to the propagation coefficient squared, plus omega squared permittivity. Okay. So this is the H, and let's not forget, H was a new quantity, which it had to be a discrete value. The discrete values, we see it in here, in fact. So that's where the H is, and let's see now what is gamma itself. So here we have that gamma is equal to A squared minus omega squared mu permittivity. This is the square root. And then this expression, this is valid for both the Tm and TE wave. So again, let's write here for a moment. This is the square root of m pi over a square minus omega square permeability times permittivity. So this was the discrete values of the H. And then we said that, so it looks like there is from this expression, it looks like we have a cutoff frequency for the waves. So apparently we have a cutoff frequency for the waves, which appears, or it makes itself, so this cutoff frequency, we denote this one as F cutoff frequency as a function of m. Okay, this is the cutoff frequency. And this happens whenever this gamma is equal to 0. Okay, so apparently, this is, so we should not forget this, then this configuration, then we should remember that the frequency is here. The cutoff frequency of a specific waveguide, it reflects itself in the omega, because we know that the omega is 2 pi f, okay? And if this is the cutoff frequency, this is the case. But then, so one thing which often it appears a little tricky to students is to understand that the waveguides have a cutoff frequency. But the big question is this one: which cutoff frequency for what? Should the frequencies, if there is a cutoff frequency or a threshold frequency, does it mean that we allow frequencies which are smaller than the cutoff frequency? The question is this now: should the frequency be smaller than Fc? Or should the frequency that can propagate through the waveguide should be larger than Fc? Do you have any opinion for so far? Which one do you think is the correct one? So this would mean that you'd have to select with a 50% probability between this and this, if you don't know much. If you don't answer whether you have to pick for the first one or the second one, you can tell me what would be the procedure to decide or to determine whether the waves can propagate through a waveguide. So one thing, we mentioned it here actually, which is very essential. So we want this gamma to be purely complex number. When is gamma a purely complex number? So gamma is a complex number. It's a, I think, let me say it this way. So it's a member of the complex number set. So gamma, this is wrong. So we just need to write here, it's a member of the complex number set. 4, so when this number is negative, right? So this h squared minus omega squared permeability times permittivity, this is smaller than 0. So we can write this one as h squared. This should be smaller or larger? Omega squared permittivity. So this condition of H being, gamma being purely complex is satisfied in this case. Then we say the following, we can take the square root of both sides, we get that H, this is smaller to 2 pi f mu permittivity, this is the square root. And the H itself is equal to, so let's have a look at H. H is, because this is Hx, right? This is n pi over a, so we get here m pi over a, this is H. We want this smaller than 2 pi f permittivity, okay? Then, what we can do here is we can cancel both sides of the pi, and then this implies that the f, or the cutoff frequency, because this is on the larger side, this is larger than n over 2a times 1 over mu permeability. So this is, now, actually this is wrong. The frequency should be larger than this, because, and this means that the cutoff frequency, the Fc, is equal to m over 2a times 1 over the square root of these parameters. So it looks like a waveguide, it serves like a high-pass filter, okay? So this is like a high-pass filter, because this can allow only frequencies which are higher than the cutoff frequency. So this is the essential logic which can be used for the, wait a second, for the waveguides and the cutoff frequency. Do you have any question for what we did so far? So we just have to figure out that we should remember that the h is a discrete value, so this is equal to n squared pi squared over a squared. So this is the discreteness of h, and then we say that we want the h to have the same value, but we want this number to be smaller than 0, and this is the logic that builds up. Now, we can use, and what we see here is also the fact that the cutoff frequency, it includes what elements, what numbers are those. So m is a number which goes from 0 to infinity. Let's see, it is 0, 1, 2, 3, 4, 5, etc. A, it is the distance between the two plates. So it starts from here down to here. So this is the distance A. And another thing that we can add is that it looks like this number, this square, this is smaller than 0, only if the frequency is larger than some specific value. But assuming that the relationship of the lambda with the frequency, we know that this would be equal to the propagation speed, the UP, right? So if this is a constant, then this means that if we can allow the frequencies which are higher than some cutoff frequency, then this means that the wavelength that can propagate should be smaller than some cutoff wavelength. So this is somewhat the inverse. So these are the propagating waves. And let's see for a moment. Yeah. So in principle, the lambda should be smaller than lambda c. The exact expression here would be the following. So we have, let's write here again, or no, we don't need it. So the FC is written right there, and the lambda, the cutoff wavelength, which we can denote this one, the cutoff wavelength C, as a function of n. This would be equal to the propagation speed, the UP, divided by the cutoff frequency. And here, the propagation speed, it is 1 over the permittivity times 1 over the frequency here. This is equal to 2a, so we are writing it from here, times square root of permeability times permittivity divided by n. Now, this is how the wavelength is going to be, and here we see that the wavelength is going to be 2a over m, or simply we can write here lambda Cn is 2a over m, where m, it corresponds to the mode, and a is the distance between the two plates. And so this is the value for the cutoff wavelength. But another thing which we should not forget is the following. The wavelength that can propagate, it should be larger or smaller. Who can answer this? Then this should be smaller than the cutoff frequency, sorry, cutoff wavelength, but this means this should be smaller than 2a over m. Okay, then so let's assume for a moment let's assume that A is equal to 1 centimeter, okay? So this is the distance between these two plates. So this is A. And then let's see which wavelength can propagate this waveguide, which is made of plates which have a distance of, so let me denote it like this, and similarly we have a plate which is going to look like this. So let's assume that lambda 1 equal to 0.5 centimeter, and another lambda 2 which is equal to 0.25 centimeter, lambda 3 is equal to 4 centimeter, and lambda 4 is equal to 2 centimeter. Okay, so these are some given this distance between the waveguides. Let's have a look. If lambda 1 is 0.5 centimeter, let's look if this one satisfies this condition or not. So maybe it's better if we write it like this. So it looks like this 0.5, which is the lambda, so let's say lambda 1 is equal to 0.5 centimeter. And we have to ask this question. This is questionable. Is 0.5 smaller than 2 times 1 centimeter, which is A, divided by M? Then, assuming that M can be 1, this looks like that 0.5, this can propagate in our system, okay? So then, we just check whether this is true. We say, yes, it's true, and this would correspond to a wavelength which is going to look like the following. So this is 2 times 1. So then here we would have the wavelength is 0.5, this is 1. Is this correct? No, it's not correct. Because this wavelength, this wavelength, if we draw it like this means that this is 1 centimeter, but it should be half of that. Let me correct this one. So this is 1 centimeter, this is 0.5, and we need to have, this is wavelength 0.5. And again, okay, so this would be a wavelength which apparently fits into the waveguide. Now let's see the other one, which is lambda 2 is equal to 0.25 centimeters, 0.25 centimeters, and let's not forget, this is for the propagating waves. So this 0.25, is it smaller than 2 over m, where m can be 1? We say yes. So then what is this wave? This second wave, which is the second one, this is 1 centimeter, half is 0.5, this is 0.25. So here we have one wave which looks like this. Okay, we say yes to this also. Then we look at the lambda 3, which lambda 3 in this case is equal to 4 centimeters. This is another wave. And this 4 centimeter, we still ask the same question. Is it smaller than 2 over m? Which, let's assume m is equal to 1. This is not true, because we're asking for this one. So we say that this is not possible. So a wavelength or a wave with a wavelength of 4 centimeters, if we try to draw it, this is going to be something like this. This is 1, 2. Now this will occupy a lot of space, but let's assume that this is 1, 1. This will be somewhere like here. And this distance is going to be like 2 centimeters. And the wave length, which is, if this is 4, then half of the wavelength is going to look like this. But apparently, a wave, now, this means that since we have only this as a waveguide, this will start here and end here. So apparently this is impossible for this wave to be sustained here. So then we say simply that this is not possible. Why? It's not possible because it doesn't satisfy this condition. Okay? And let's get the other lambda 4, which is equal to 2 centimeters. And the question is again, is it smaller than 2 or something? So let's assume n is 1. Then we can say that this condition is satisfied. Okay? Because this would be smaller or equal. So we say that this is possible. So the fourth wave, when lambda is equal to 2 centimeters and the waveguide is just 1, this would mean that we'd have a case which otherwise would look like this. But forget of what we draw down here. So it's going to be that so this wave, the only wave which is not supported is this one, which is lambda 3. But all the rest they can be supported. So you take this out, and one way to represent this, it would be the following. But it looks like when lambda is equal to 4 centimeters, this is larger than the boundary condition, and in a very folkloric way, we can say that this wave it simply does not fit. Okay, because the waveguide it allows apparently wavelengths which are equal to the distance between the two plates times 2. But if the wavelength is larger, it will simply not match, not fit, right? So sometimes for students, you can use both techniques, but often students might find this approach more intuitive, because they can simply say, well, it doesn't fit. I mean, the wave is bigger than the waveguide, so you keep it out. Or, this is one way to think about this. Another way is you can simply call them as a high-pass filter, which means that it is going to allow only frequencies that are larger than the cutoff frequency. Do you have any questions for the material discussed so far? Okay, we can have a short break now.